You're going to get mighty friendly today. These rooms aren't designed for so many people. Typically it's me. So this is what we call the dirty lab. It's where we do all the dirty stuff. So you'll notice the floors are slick. Be careful. That is some sort of powder, whether it's from that room or it was from us machining something, using the table saw. It gets slick. These are asbestos floors, so we can't cut them up or anything like that. So they're going to stay there. A lot of what we use in here is foam. You can see under the table there's a bunch of pink foam. Our foam is heavy and hard. It's not like the sort of foam you would typically think of as being foam. So we pick foam dependent on what it is that we want to do with it. So if you feel these guys, these are different densities. And it's all about choosing the right material for what you're wanting to do. So if we need to do a big model that needs to be handled, you pick a lightweight foam. If you're going to do some thermal forming on it, you need to consider, of course, the heat that can go into it. Some of the foams hold a better edge than others. It really depends what you're going to do with it down the road. And when you buy the foam, you're typically buying it by the weight per cubic foot. So you specify, I want a 2-pound foam or a 30-pound foam. Doesn't matter. And they just ship it to you on a pallet. So what do we cut the foam with? The CNC machine in the corner there, that is the CNC router. It is good for 3 dimensions. So it's got X, Y, and Z travel. We do a lot of molds on it. So let me grab some molds. One of these. So one of the community college classes we taught, one of their projects was to make a RC boat. So this is the hull of the boat. It started out as a block of 2-inch foam. We cut it down, primered it, and then made a fiberglass tool off of it, and then pulled down carbon fiber hulls to make a carbon fiber RC boat. And one thing that we do somewhat frequently is make glorified dog bowls. So this is a tool that's designed to pull down in the vacuum forming machine. And what it is, so throughout campus there are lots of spin coaters and little centrifugal things. Well, some of the fluids that they use inside are extremely expensive. Maybe they have gold in them or some sort of life that they grew to be in that fluid. So when it gets cast off onto the side, a while back they were just taking a paper towel, wiping it out, having to throw it away. So people got to thinking, okay, RapidTech's on campus, they got to figure out something to fix that problem. So what we did is I went into a couple of clean rooms and I took some cardboard and some scissors, and I traced the profile of the spin coaters. And then went into SolidWorks, made a really simple revolve, and then we cut it out with a CNC machine. And then we would vacuum form it out of a sort of sterile plastic. And now they can put this coat inside the spin coater. And when their stuff shoots off to the sides, they just take out this plastic, basically condom thing, they squish it, and they can pour all the fluids back in. So it allows them to recover that material that before they were throwing away. It's kind of a neat use. It's easy, cheap. Some of the other tools in here behind you guys is a gray thing with a big acrylic lid on it. That's a vacuum chamber for when we're doing mold making for silicone or urethane. So if you take a silicone or urethane, it's typically 2 parts. Pour in one part, pour in the other, and then mix them up. Well, anytime you mix them, you're going to whip air into it, and you don't want air into it when you pour it, because that gives you poor surface quality and non-homogeneous material. So you put it in there, close it, and you suck all the air out of it, and when it tries to equilibrate, the air trapped inside that material goes out into the chamber. It's kind of cool. The silicone and urethanes, they bubble up, and they can almost triple in volume sometimes. And then once all that air escapes, you turn the vacuum off, the air goes back in, and you've got a much nicer material. And if you want to be particularly careful, you would use this thing, which is the opposite direction. This is a pressure pot. So we hook it up to shop air, and you increase the pressure inside. So if there are any bubbles left, the pressure inside is so great that it just crushes them down. So once your material cures, you've got little tiny bubbles rather than big bubbles. Unfortunately, that traps stress into the parts. So if you take it out too early, that bubble expands again, and your part just does really weird things. So you always make sure everything cures. Some of the cure times can be 24 hours, so patience is a virtue. But it's pretty much a set and forget thing. It either works or it didn't work. But unfortunately, you gotta wait 24 hours to find out. And you can't get that time back, because if it didn't work, there's no repairing it. It's just do it again. Okay, so we're gonna change rooms. All right, so this is a fused deposition machine. So FDM. This is the one that uses extruded ABS wire. So this is the technology that you see the most of for low dollar amounts. The reason being, the patent just expired on the technology. The thing that hasn't expired is the fact that it's in a giant box. So a lot of the machines that you see for like 1,500 bucks online, they're always out in the open, or they have just like a little stick figure box, but they're never sealed. That's because the sealing patent still exists. That may sound kind of silly, but that's what makes the more expensive machines so much better, is they have much tighter environmental control over what's going on. Right now it's printing cases for the Raspberry Pi computers, those little tiny, kind of like an Arduino. It prints in two materials. So there is the white material in our case, which is the ABS wire, and the brown material, which is the mystery material. The mystery stuff is a support. So you consider this thing works like a hot glue gun. So it takes the spools of wire, it heats them up, and it squirts them out of the head that's jogging back and forth up there. Well, if it's hot enough to liquefy the plastic so it comes out, it's not going to be strong enough to support its own weight. So you need some sort of support if there's too much of an overhang. Typically it's around 30 degrees. So what do you do if you've got all this extra brown material? Well, you can break it away, and on some of the lower end machines it is designed to be broken away. Or you can put it into a special tank. And the tank we have is at the back of the room. It's just a silver heated tank, and it's filled with sodium hydroxide, which is a base. And this stuff is designed to dissolve away in sodium hydroxide. So when you're done, all the brown stuff's gone, and you're left with your model, which allows you to do, I can pass that around, more complex geometry like this. This was done for Spawn or Span architects out of Austria. Obviously this is a piece that you could not cut on a machine. This would be very difficult to make by hand. All sorts of general nastiness. And when this was printed, it would have been just this huge mess of the brown material supporting all these little geometries. And this whole interior cavity would have been filled. So that gets thrown in the tank, you wait a while, you come back, and voila, it's done. That waiting a while part, depending on the geometry, it could be an hour, it could be a couple days. Depends on how fresh your chemicals are and how nasty the geometry was. So if you've got a really deep but small diameter hole that it had to fill, it's going to take a long time because that liquid has to penetrate through all those layers of stuff. Let's see. It is capable of printing in other colors, but these machines print one color at a time. So you can buy a red, a green, a blue, a yellow, whatever. They are capable of relatively fine detail. Here's some iPhone 4 cases. This one is made out of material called Ultem. It's not printed on this machine. This is a high temperature, high strength material that they use a lot in aerospace. They do it for a lot of tool making, fixturing, things like that. And this is just normal ABS. But you can see some of the detail. These machines typically are lower resolution than a lot of the others. This particular machine only goes down to 10/1000ths of an inch, so 0.010 inches per layer. Almost all the machines in this industry, when they say a resolution, they mean the Z resolution, so the height per layer. This is 10,000ths. Some of the other machines we have are 3, 4, or 1,000th. 4 is kind of the common one. There are varieties of this machine that will print a 3 foot by 3 foot by 2 foot build volume, so they can get pretty big. This one I think is around 10 inches by 10 by 12 or so. It is possible for this to run unattended, and unlike most of the machines, if this runs out of material, it hits pause and it lets you know that it ran out of material. You can put another one in. Unfortunately, a lot of our other machines, they don't know that they ran out of material. They just keep running. And they don't know that they've crashed, so they'll just keep squirting junk all over the place. So that's one of the nice things about this particular machine, is it's pretty aware of if it's screwed up or not. Because if you're doing a 96-hour build, it's good to know if it's just printing air or something like that. Anything else here I want to show you? Because of the way this lays down material, it is not capable of doing super thin walls. So figure it's laying down a bead of material. Well, it's got to, that's like its unit of measurement. It's one path, right? So let's say it's a 10,000th path. What happens if I want to do a 15,000th wall? The machine would be like, what is a 15,000th wall? I know how to count in tens, right? So maybe it just puts down a 10. Maybe it puts down 20. Let's say you do a 25. Okay, I can put down 20 or 30, or I can put a slight gap between the two. You don't have a lot of control over that in this software. Maybe some of the higher end machines you do. But it's kind of guesswork. One of the things that you can do is print your object at a slight angle so that you get little overlap. Sometimes that works. Biggest downsides to this machine and this technology in general, Z strength can be weak. You imagine if you're printing with a bunch of round objects stacked on top of each other, it's going to be kind of weak at the bond. So it does kind of squish them a little flatter than perfectly round, but because of that, it is possible to separate them. And then speed, that head's moving around pretty quick, but the challenge is if I want to do multiples. This thing scales almost linearly in time. So if I do one and it takes an hour, 2 might take about 2 hours, 3 takes about 3 hours. Some of the other machines that we'll see in the next room scale a lot better. And one of the machines that we have in another room scales perfectly. So there's hit and misses. One of the nice things though is the material is unknown. I get to say, no, this is polystyrene, or no, this is ABS. It's not a mystery chemical that behaves like ABS. So that's an upside to this stuff. Any questions about it?
If you wanted to print something on top of something you already had, is that possible?
Not safely. Maybe on some of the other machines, you may be able to confuse it to think that there was nothing there. But typically this thing always comes down and homes itself, and it wants to start at that base layer because you're always looking for it to bond to something. So it's got to melt that first layer into the platforms that are at the bottom. So I haven't seen that done. It might be possible, but I certainly wouldn't want to try it on my machine. Maybe one of the lower end machines. Price-wise, you can find the do-it-yourself kits for these for like 600, 800 bucks, and they go up to over 100,000. just depending on what materials you want to run, how big of a platform, things like that. Okay. All right, so we're going to switch rooms. Okie dokie. So let's everybody file in. All right, so when people say 3D printer, the people in my industry think of these. We're not thinking of the other machines, we're thinking of these. So the reason they're called a 3D printer, it prints things 3D, right? But it behaves a whole lot like a regular printer. This one, in fact, uses HP print heads inside. We just go down to Staples, whatever, buy them, and then we blow all the ink out of them and replace it with this ink. This ink is actually a binding agent. It's largely water, some coloring, some preservatives and stuff. So right now, this thing is printing a bunch of little figures. It's printing these in red, green, and blue. They are incredibly brittle when they first come out. The powder is very much like plaster that is glued together. So getting things out can be a little messy, and you have to be careful if you're printing something with really fine details, like the mesh on that house sort of thing, or the inside of a skull. Typically has all sorts of little dangly bits. So go ahead and look inside this thing. This skull is made from CT or MRI data, I don't remember which. But basically, when they take a scan like that, they cut you up into a bunch of little slices. So I take that stack of images and I separate them by whatever distance I'm told they were scanned at. And then you volumize that scan. So you connect the dots in 3D to figure out what shape should have been there. The first time I did it was the first time I ever got to look inside of what a real skull would look like. And we're used to seeing the Halloween versions where it's just kind of a generic, nice and smooth. And there's all sorts of extra crap in there that I had no idea existed. And that stuff proves to be really difficult to work with because in a powder-based machine, it's not so tough. You just shake the powder loose. In this machine, you have to be careful because it's really brittle because it's so small. But on some of the photopolymer machines where it makes a hard plastic support, you got to figure out how to break that support away. So right now it's printing the bottoms of their heads. So this thing is printing with each of these laid down. So it prints cross sections this way. So in a few more minutes, it'll get up and you'll start to see the ends of his feet, like his heels. And then you'll see the arms and so forth, and eventually you'll see the face and the top of his head. Time-wise, these machines scale very nicely. So because that head's moving pretty quick and it's spraying down a swath of binder, you're able to do multiple copies at the same time. So if one part took an hour, 10 parts might take an hour and 5 minutes, sort of thing. It scales nice. What else? These are some of the only machines that do color. There's a new machine out called the Iris from a company called MCore, and it actually uses a similar printing ink sort of idea, but only for the color. So what it's actually doing is it takes stacks of paper and it cuts them out, and then it saturates them with the ink, and that's how you get the color. So it's literally stacks of paper, so it's super duper 3D printing. It is slower than the dickens. It's cheap-ish because you just go and you buy a ream of paper and that's your build envelope. But literally basically an X-Acto blade, and it goes like this and cuts one layer and then it glues the next layer down and cuts it out, glues. So while it may be more affordable to buy reams of paper, something that could be a 12-hour build on that machine, maybe an 80-hour build on the other machine. So long as you don't value your time, it's a great deal. Various other materials can be run in here. The machine, there's a smaller version of it in the back corner of the room, and it's running a ceramic material that gets fired to be ceramic-y. What else is interesting about these? They're good for concepts. You know, putting something in somebody's hand and saying, this is the idea. You certainly wouldn't want to have your life rely on anything printed on here because of the mechanical properties. You can boost the mechanical properties by hardening them. You can harden them in Epsom salts and water for this particular powder, a wax, it's a two-part kind of epoxy urethane stuff, or favorite being super glue, and also wood hardener from Home Depot. Super glue is my favorite. Unfortunately, you do get stuck to everything if you're not careful. And super glue is rather exothermic in volume. And when it kicks off, it off-gasses, and that off-gas is really nasty. Burns your eyes, your lungs, all those fun parts. We've also had huge variances in the super glue. So I don't know if any of you guys ever go down to Utopia Tools down in San Clemente, and there's another one somewhere. But they sell like generic cheapo super glue. Stuff will melt your face. The fumes are so bad. The first time I tried using it, just completely crying at the table because it just burns so bad, and your eyes are like, no, I'm just gonna cry. Like, you have no choice in this. There are others that we have used that are, they say no smell, and they're complete lies. And others that are low smell, and those are pretty good. Again, we typically buy them in 16-ounce containers or gallons. And the cool thing about super glue is it's reactive with water. So as long as you keep it sealed, it's not going to go bad too quickly. You can use it over and over again. You just gotta, take into account that it's super glue and it's going to stick to you. So, any questions about this tech?
Does it recycle the powder?
Yeah. Yeah, this machine is awesome for that. So any powder that gets used, it doesn't have like a life, so long as you keep it dry. If there were super high humidity, it would be a problem. But the powder actually acts as the support, and the only powder that gets used is the stuff that gets the ink on it. So all the stuff that isn't printed on this side, I can feed it back into the feed side. And then actually, this roller that goes across to do the layers, there's a slot there, and that slot is the overflow. So any excess powder gets pushed into there, and there's a bucket here. And I just filter that and put it back in the feed side. So you can use this powder over and over and over again, which is really nice. Keeps the cost down. Okay, anything else? All right, let's switch rooms. Okay, so this is general work purpose room and offices, but somebody made a comment about the octopus. I don't have a particular octopus fetish. It was a free model, and I could print it on multiple machines, and so you can see the surface qualities and everything between the different machines all on the same file, and it's kind of an interesting file. It is a complete pain in the butt to take out of that last machine you saw because the little tentacle things are super, super fragile. So it's one of the test parts that I have my students do just to get them incredibly frustrated as they break them over and over again. But it teaches them to be really gentle. The machine to my right is a bits for bytes machine. These are machines that you can buy online, or you used to be able to, in kit form. And it just comes in a flat cardboard box, and everything's laser cut, and you bolt it all together to try to get it to print. So like I said before, a lot of the inexpensive printers, they're all out in the open because that enclosure's a no-no. But it's the same idea. It has a spool of ABS wire, feeds it up, heats it up, and pushes it out through this little extrusion nozzle. So we bought two of these. We had a local high school build one. We built the other. The goal was to take them around to demonstrate at high schools, get people interested in the technology, so forth. I personally wouldn't buy this one again. one of the downsides to a lot of the kit printers that are made out of thin acrylic is that they're rather fragile. Acrylic is a brittle material, so if you over tighten a bolt, it breaks. So this one's a little flipsy. What else do we have in here? So on the table behind you guys, there is what's called an up printer, the little black guy printing. It's making little rocket ships. We now use that one a lot for outreach because it's small and it's easy to put in a bag and carry somewhere. We also have this device, which is a laser scanner. I will turn it on so you can see lasers shoot out. These are eye-safe lasers, so don't worry about it hitting you in the face. We have scanned some of the other students. So you just get them to sit nice and still and scan, and then touch up like mad. You have to sit wickedly still. It's ridiculous. So if you can see it, there's two beams on top right now, and there's some cameras whirling around and they're taking pictures of those beams. And then comes along another set of beams that are slightly closer together. And what it's doing is making sure there's redundancy in the data. So if I were to bump the table, the first scan is not going to quite align with the second scan, so it's going to throw out that data. But anything after the bump where it was nice and smooth should work. So laser scanning is great for reverse engineering stuff. In this case, it was a handle for a paddleboard company, Hobie, that makes it. They had mocked up the original one out of fiberglass and Bondo largely, and they wanted it to be perfectly symmetric and make some adjustments to it. So we laser scanned it and created the files necessary to make the tooling for the carbon fiber one that's there. And it only takes, if you've got the time, a couple days to do that. And you can knock out iteration after iteration in between to get it exactly the way you want it. There are two old radios there. I want to say these were from the 30s. They're actually vacuum tube radios. Why do we have it? So the one on my right, that faceplate is all messed up. And that's not because it caught on fire or something. That's old age. So the chemistry in the plastics from the 30s wasn't so great. And what was an inexpensive radio back then got mystery plastic. And that was the ravage of time. It just warped. So there's a gentleman locally that is part of an antique radio collection society. And they wanted to recreate these things. So they go through and they restore all the cabinets, but you can't restore that plastic if it's that bad. So we can laser scan it, or you can send it out to get CT scanned, something like that, and then reverse engineer it. And we've created replacement parts for various radios at this point. The odd piles of clear food, actually a cool product. There are two women locally, and they had this thing where a lot of stroke patients lose the ability to eat solid foods, so they need to eat purees. Well, it's kind of disheartening if you're, an adult that has to eat baby food all the time, right? So they got together and decided to create purees that didn't taste like baby food, taste like what you were looking at, and actually looked like real food. So we helped them through the whole molding process of creating the tools necessary to make molds that would create these real looking foods again. So they've got, broccoli and chicken and meatloaf and peas and corn and lasagna, rice, macaroni, all sorts of things. It was a pretty crazy project because somebody comes in with a pile of rice and is like, I want to make that. Like, okay, But these two ladies were fantastic to deal with. And you know, it's a product that I like because I love making things where there's a use. You know, there's something in mind that's going to help somebody. You know, yeah, I can make a Wii controller, or we can do that. And coincidentally, we did make some of the prototypes for the original Wii controllers. They used us to print them out. They were monstrous, like Wii controller. And then they pared it down until you got the nunchucks that everybody's used to. I'm going to grab one more laser scanner real quick. It's in here. This is the variety of laser scanner you are most likely to see on television used incredibly inappropriately. They're on TV because they look cool, right? You pull the trigger and laser beams shoot out. You can wiggle it around in space and it scans stuff. It's $3,000, around $45,000. These are great for bigger things and where you need high portability. So imagine if I was having to recreate David or something like that. I can't touch David, but I can put a ladder next to it and walk up and down and scan it. So that's where something like this really comes into play, because something like this needs to be on a table or a tripod. This just needs to be connected to a laptop. One thing though, one of the greatest uses that I've seen, it was on CSI or NCIS or something like that. Muddy footprints in the rain is what they were scanning. BS, because you need to cover whatever you're scanning in reflective white stickers. So how you would apply reflective white stickers to a muddy footprint and not damage the footprint is questionable. But it's fun to use because you look like a rocket scientist or something. Not so fun to use though. It is good for scanning faces. We do a lot at Outreach because you can involve multiple people. You can have one person doing the scanning, one person putting stickers all over the third person that's sitting there. The light is wickedly bright, and you always tell people like, it's going to be bright, just close your eyes. Close your eyes, you're like, oh God, it's bright. This one you could keep your eyes open and it's bright, but it's not, oh God, it's bright. But it's fun. And then telling them not to drop it because it costs more than their car. It's always good. All right, other things, silicone mold making. You know, it's not additive, but it's really useful and it extends the life of what you can do with additive. So sometimes we will print parts of a mold. So these are printed out of wax. And all these are the tools necessary to create the other side. So you would print both sides and you get this sort of mold. And it's got all the keys in it. It's got all your vents and sprues and your gating. And they just snug together. And now you've got a nice silicone mold. The reason why you would spend the time to do it this way is that to do this manually, you would have to cast twice at least. So you would make a board with a bunch of little plastic pieces stuck to it. And you would sit there with wax and do all this sort of stuff on the board. Then you cast it. Then you would flip it over and you take off the backing board, and then you do the work for the other side, and you cast it again. So depending on the silicone, that could be 2 days or more of work, versus if I design the part on the computer, I can design the tools on the computer too. I just hit print and print the tools, and I can pour both at the same time. So it is more expensive to do, so long as you don't include time. If you include time, this can save money. This is what a pile of macaroni looks like as a mold. And kind of interesting reverse engineering project. So if you guys ever go to the Capitol Mall, DC, and you look at all the lamp posts that they have around, holding them to the concrete bases are these things. Okay? Not terribly glamorous, they just sit there and cover bolts. People were stealing them. Why? Because it's metal and you can sell scrap metal. All the tooling to make these is gone because these puppies are old. So they sent us some and said, okay, can you guys recreate this? We're like, yeah. So we painted them white, covered them with little red dots so we could align things better, and laser scanned them. And then we gave that data back. They actually printed a tool and then injection molded a bunch of plastic ones. So now they're printed out of plastic and made to look like the old metal ones. One of the funny things about it is on this spot, somebody hit it with a hammer or dropped it or something. So there's a flat spot right here. Well, it's a laser scan, and they printed exactly what was laser scanned. So every future version comes pre-dented. So it adds to that authenticity. But that is one of the things about scanning is if you've got the money, there's product out there that can give you fantastic results. There are $100,000 scanners which have high enough resolution to pick up the raised ink on a dollar bill if you just set it on a table and scan it. And that scan can take 2 seconds or something like that. So it's not down to, you know, the crazy submicron level stuff, but you're not going to print at the submicron level anyway for the most part. So any questions about the stuff in here?
Explain the red dots more.
Sure. So because the scanner, a scanner that sits on a tripod is unable to see around a corner or anything like that, if I scan this object, I'm going to scan it from this angle, and that will give me this swath of data. Then I'm going to scan it from the front, and that will give me some overlapping portion of data, and then from this side. So I can use these red dots and say, okay, this red dot was in this scan, and then it was in the next scan. So I tell the computer that point's the same. So long as you do that for 3 points, you get a nice triangle, and it's able to figure out where those go. So on something where the geometry is changing fairly nicely like this, probably didn't need the dots. It's just a nice to have. It's like a crib sheet. On something like a door panel that is really smooth, the computer's not going to know how to match those together. It's just sees smooth. So you can get things where it would have one scan over here, one scan over here, and instead of being like this, it'll be like good enough. It'll just overlap it, which can do really horrible things to geometry outside of those scans. So it's always good to have some sort of visual reference as well. Another thing you can do, some of the programs we have are designed to work with ping pong balls. So if you're scanning a person or a car, the ping pong ball is a nice geometry because you can look at it and go, well, humans aren't made of ping pong balls, I can get rid of that. So you put ping pong balls on people and you scan it and you tell the computer, okay, match up the ping pong balls and then delete the ping pong balls. So it uses those as the reference. They're nice spheres, puts them all on top of each other, and then they disappear and you're good to go. So if you can't have a visual reference, some sort of tactile reference is also good. Any other questions? All right, so there's weird stuff all over this room. So biggest piece of equipment, CNC machine. We talked about those yesterday. That is a 4-axis machine. It's made by a company called Tormach. It was the machine that was able to fit in the elevator. Does a decent job. It's got some goofy things that I don't care for, but it works. So why do we have that if we have all this additive equipment? And that's if we want to use real material, right? If I want to be able to specify I need something that prints in acetal, well, there aren't machines that print in acetal, but I can cut it. Or if I want an aluminum one, well, a machine that prints in aluminum in the additive industry is about $1.5 million. That machine is about $17,000. So a couple orders there that I would much rather have a $17,000 machine if I'm just going to cut aluminum. Also in here, this is a CMM machine. It's coordinate measuring. So prior to laser scanning, we just poke things with little sticks. So this head comes down and it pokes things. So they're great for verifying known geometry and telling you how far off it is from what it should be. So these are used a lot in industry to check mechanical parts, rigid parts. So if you knew that I'm supposed to have a hole right here and it's supposed to be this big, this machine would come over and sweep around that hole and tell you how far off it was. Yeah. What else? So laser scanning project, Kawasaki. We talked about this briefly in the lecture. Here's a motorcycle. It's an off-road bike. They don't need a helmet for freaking A. They need helmets. They don't need headlights. So we took a headlight. This is a headlight. We spray painted it gray because lasers do not like clear objects. They don't like shiny objects. They don't like sharp objects. This was all of those things. So gray spray paint works great. The dots, again, for reference, not needed, but liked. Printed it out on the Z-Corp machine out of the plaster material. We said, hey, plug this into the hole in the front of the bike, make sure it still fits. They said it did. Can you poke a bunch of holes into it? Yeah, we can do that. I can poke holes all day long. So we poked holes. It made it lighter, and more air could blow through it. I said, good, make us a plastic one. So we printed plastic ones. This is made on the FDM machine that you guys first saw. It is actually just white plastic that's been spray painted black. They were able to race all season with it. It's pretty tough. And one of the things that I like the best is in the promo photos, I just photoshopped these together from stills that they made. But obviously they use big old fancy cameras, and there's enough detail in it to see that on all the promo photos, it is just that stupid part. They didn't sand it, they didn't finish it, it's just spray painted black and thrown on the bike. So I get to point to it and go, that was mine. Also in here, laser scanner. This is another one. Obviously this one is bigger and tripod based. This is greater for things human-sized, cars, buildings, things like that. Pretty much never use it. There are a flock of little haptic arms up here. These are, let me see if I can unplug it. These are devices for sculpting virtual clay. They're used a lot in art, animation, and the medical field. So this thing allows force feedback. So you have a ball of clay on the screen, and you can poke at it, and you get to feel where it is in three-dimensional space. Some people think that's pretty awesome. Others that I know that have worked with clay for a long period of time think it's an abomination because the clay doesn't feel right. It feels like virtual clay. It doesn't feel like real clay. These puppies are expensive. They are somewhere around $40,000. Or they were at one point. There are different flavors of them from the teens on up. But they're interesting. So one of the other reasons to have a CNC machine, you guys saw the CNC router earlier, are projects like this. So I'm a skinny guy, 6 foot, $130. Not a whole lot of body armor fits me. So I have the tools to make custom fit body armor. So I rolled up my pant leg, put little stickers on my leg, and laser scanned it. And we were able to cut it out of, this is 3-inch foam. And then make a fiberglass tool and pull down Kevlar shin guards, basically. They fit really nice. Absolutely not worth the time to do it. But it was a cool thing to say, I could do that, and it got me a master's. So that was nice. I also made it fancier by embedding RFID tags in there that said things about your health and things like that. But the whole point was mostly so I could make myself Kevlar body armor. And then a bunch of cutting and measuring tools on the tables, things like that. Outside the room, there's a little vinyl cutter. We use that to make stickers and warning labels. There's also a rack full of carbon fiber and Kevlar. Some vacuum pumps, things like that. Just all different projects. We got to figure out where everything goes, so we fit stuff where we can. So any questions about the stuff you see in here? All right, next room. Okay, so this room has 3 SLA machines. It's stereolithography apparatus. So lithography, it's making a print of something, right? So you see a poster, that's a lithograph. Stereo, it's in 3D. These guys work by having a laser up top. So in this case, it's a 1-watt UV laser. It shoots down onto a liquid. This is a very thick, kind of syrupy-like liquid. And this is DSM 11122, which means it's a Class 6 certified acrylic-based resin that can be polished to be water clear. So why is Class 6 important? It means it can be brought into an operating room. So it's not good for putting inside somebody unless you dislike that person. It is good for being sterilized and used as a reference. So I showed the pictures of the skulls that were clear. That's what came out of this machine. Here's one. So why print it out? This one was just rattle can with spray paint, so we're going to ignore that part. But if I can print this out, the doctor can form all of the plates necessary for surgery onto this nice hard plastic model. This model is accurate to within a couple thousandths of an inch, so it's going to be plenty accurate to fit onto somebody. Previously, they would cut you open, make you look like the Predator, and then they would hammer the thing basically onto your face till it fit, and then sew you all back up. So if they can skip that whole make it fit thing, that's huge. It means you're open for less time, there's less trauma, and everything already works. Yay! So good use of this. The other thing that can be cool, we've had people come in from rollover car accidents where half their face was pulp. So you take the medical imaging from the good side of the face. You use your fancy computer and you mirror it over and you print out the other side of the face. So now the doctors know what the other side should look like. They can build all their scaffolds and tools off that model and replace all the mangled bits. It's a good use of this technology. There are machines that you will see later. The bigger versions of them are capable of printing those face parts directly for implant, versus this would be used as a reference for implant. So the 3 machines here are kind of redundant. This machine's good for printing bigger pieces, where the other 2, same technology exactly, just smaller pieces. The middle machine is running DSM 9120, which is a, oh damn it, just finished. Which is a polypropylene-like material. I had it running so I could point at it and you guys could see the laser going. Literally just finished as we walked in the door. That sucks. What you would have seen is a blue laser doing this. It really does just look like a laser pointer that's wiggling back and forth really fast. It's a UV laser, so what you see is mostly purplish. And wherever that laser hits that liquid, it turns to a solid. Because I'm printing in a liquid, I need a support structure. So the software or you create a support scaffold for these parts. This stuff just gets broken away and thrown away. So there is a bit of waste. It's pretty negligible because these things tend to be about 600 microns thick, so it's pretty thin. This machine uses a heavier support than those. That one uses, it's almost hair-like to hold things together. These machines are terrible for doing big, thick things, okay? So you can imagine if I asked you, or more than likely you asked me to make you a brick with a hole in it, I'd say, okay, layer by layer, I need you to draw me what those cross sections look like. And I give you a pencil, and it's a wickedly sharp pencil. And so you draw the outline. I said, no, that's the outline of a brick. Bricks are solid. Shade that puppy in. You'd have to sit there and do this. That's how these guys build. So if you've got a spot size that's like 10,000ths of an inch, and it has to sit there and shade in a brick, it takes forever. So you never want to do big old honking things. Thin walls are great. Versions of these machines are able to create very small parts, like ant size. There's a company called Fineline that custom modifies these things to do very small stuff. But most people just run them at either 4,000ths layers or 7,000ths layers. There's a wide variety of materials. There's clear stuff, there's white stuff. I saw one company, DSM, had a flavor of resin that even in like a 1/4 inch thick, it would stop like a 22 round. So they do have pretty cool stuff. One of the downsides, a lot of the chemistry is kind of nasty. So they are acrylic based, which is a sensitizing agent. So the more you touch it, the more allergic to it you become. So anytime I'm touching the liquid, I'm always wearing gloves. Anything that comes out of these machines gets washed in a tank that's over there, and then it gets placed into one of those 3 rectangular boxes in the back. Those are UV ovens. Think cat-sized tanning salon. You turn it on, it's just glowing lights everywhere. And all that does is finish curing the resin that's on the surface. With the right coating, these things will last quite a bit of time. It's my understanding that the FBI has parts that have been in the field in LA area for more than a decade. You just never know they're there because they're made to look like something else, and they hide cameras and things like that. Temperature range, not great. These particular resins that we have go soft at around 120 degrees Fahrenheit. So it's not something you want to put in a really hot area. You might notice that our F-22 is kind of floppy. That's because it got a little warm in the back of somebody's car. So the wings drooped. Color-wise, nobody would want this color. This is an ugly color. I don't know what color this is, but I don't want it. When it came out of this machine, it was blue and it was clear. So why is it this color? Age. It has been continued to be exposed to UV light, so it has continued to age and harden. All the lights in this room, underneath the coverings, there are actually secondary coverings around every single tube that block out the UV light. Because people don't think about it, you can get a suntan from these lights. It just takes a long time. These put out a broad spectrum that includes UV, and stuff like that would ruin these models. But you can clear coat this stuff with a UV clear and you're good to go. Any questions about these 3? Okay, we're going to talk about the laser cutters next then. So these 2 laser cutters, they operate the same way. This is a 25 watt and this is a 60 watt. This is a 24 by 18. This is a 32 by 18. Probably some of the most used tools that we have because they're ridiculously easy to use. So if you guys have ever used Illustrator or Corel Draw, you could run one of these machines because it prints directly from those. And you literally file print and it sends it just like it's going to a printer. The difference is this is a flamey printer and it cuts things. They're good for cutting through things, but without a lot of work, you're not going to cut to a certain depth. So you couldn't tell it, cut a 1/16 of an inch deep. It's just going to go all the way, or you can sit there and fidget till you figure out what power range 1/16 of an inch deep is. This is good for plastics, woods, things like that. This one doesn't have enough juice to do big metal parts. Water jet's typically good for that anyway. But you can make random fish, business card holders, little Mayan calendars. And then what is it used for the most here? Probably civil engineering. They use it a lot. The microfluidics groups and aerospace. So the solar plane people, the design, build, fly, Mark's microfluidics groups, they do a lot of stuff that's based on CDs. So they'll use these machines to cut CDs, and then they have bonding agents that hold them together. So you would create the geometry that you want in multiple stacks, and bond them all together to get the shape that you want in the end. And then civil. Some of you may have seen the group that does the earthquake building. So they build like this 50 or 60-inch tall structure, and they put it on this plate that gyrates around, and they see what level they can abuse this building to before it falls apart. So a couple years back, they were doing it, and they were cutting all the parts by hand. And they came to us to see if they could use our table saw to cut things. I'm looking at like, wait, you have to cut how many of these? And they're all going to be this big. Why don't you just use the laser cutter? So we would take an object. So rather than cutting this shape by hand a couple hundred times, I would just take a DXF, put a couple hundred of them, and tell it to print. And the laser sits there and cuts them out, cuts them out, cuts them out. So it'll take a couple minutes instead of a couple hours. And all the parts are pretty well the same. There's a bit of variance because of the wood, but it's certainly more accurate than, you know, a kid 24 hours into it, just surviving solely on caffeine and willpower. So it's a good use of the technology. The only thing, anytime you're cutting something like this, you're using the laser. It's probably on fire, so it's not something you want to do and then leave. I have set this machine on fire. I melted the entire lid into it while doing a tour, which was awesome. It was one of those things where, yeah, you just set it up, you hit print, you go away, and then I come back, and the whole lid's melted in. There's smoke everywhere. And one of the students is like, is it supposed to do that? I was like, no, you rocket scientist, it's not supposed to do that. Come on. So at that point, you're waving around, hands on fire, just trying to figure out how to shut it off. So yeah, it's keep track of what you're doing, of course. But if anybody wants to use these, it's basically super easy. It's inexpensive so long as you bring in the material. A lot of times we just buy the material from Home Depot or Industrial Plastic Supply or anywhere. Because so long as you know the thickness, you can get it to cut. There's some materials that you don't want to cut. You don't want to cut PVC. The C part is not what you want. You get chlorine gas. Things like Lexan, various polycarbonates, you can cut them if you're very careful on exhausting all the stuff, but they produce some nasty, nasty fumes. So we have a high power exhaust vent over there, and sometimes you'll see it, we'll have the window open, and it'll be flopping around outside really energetically. Our old one was pretty weak and it just kind of went, and this one is like, nope, everything goes. Any questions about this tech? Okay, we're gonna look at the machines in the back. Okay, so this machine is old and it looks that way, and it's very simple. It squirts out wax. We take a tub of wax, and it literally is just a tub of wax like this, and it heats it up and it liquefies it, and then it squirts it out of a bunch of tiny little heads. And so there's a big head with tons of little heads, that just goes back and forth, depositing it. And then there is a really scary bread roller thing that's got a blade on it, and it's a milling head. And that milling head spins and it goes over the surface to make sure it's nice and flat before it deposits the next layer. So drop by drop, it builds your objects in 3D. And it prints out some pretty nice detail on the upsides of things. The downsides of things are terrible. The reason being, it's only got one material, it's got wax. So if I have to remove a support that is the same as my model, it's the same as the model. How do you tell them apart? You got to scrape it off. So typically a part comes out of here and you put it in a refrigerator, and that makes the wax really brittle. So the support, which is a bunch of little wax trees, is hopefully more brittle than your model. If you put it in the freezer, your part will probably explode, so don't do that. Refrigerator is good. Why would we want to print in wax? It's the investment industry, casting. So one, it's good for silicone mold making because silicone doesn't stick to much, but it definitely doesn't stick to wax. But a lot of the casting industry and foundries. So it is perfectly possible to give somebody a plastic part and say, hey, make a mold off of this and burn it out and pour my stuff. Unfortunately, or fortunately, we live in California, and California cares about air quality. So most places don't like you burning ABS or mystery acrylics. And most foundries don't want to mess with that stuff. If I have to give you a 50-page document and say, okay, this is how you behave for this piece of plastic, versus I can give them a chub of wax that they've had for centuries, it's a no-brainer. They want the wax. So you print it out of wax, you coat it in ceramic, you let the ceramic harden, you melt the wax out, and now you've got a cavity in the shape of whatever the wax was. You then take your molten metal, you pour it into that cavity, you let it harden, hit it with a hammer, the ceramic breaks away, and you've got your metal part. So it's one way to create low volume things where you need a lot of detail, like jewelry is typically done via investment. And then like custom tools or just fancy things. This little guy to my right also has the ability to print in wax, but it does so in a trickier fashion. So inside there is a little tray, and this little tray gets filled with a mystery material that is light sensitive, which is why this thing's orange, so the light doesn't get in there. It's UV sensitive, and down inside there is a DLP projector, just like you would see in any classroom. So rather than a laser having to sit there and do this, this thing projects the whole layer at once. So earlier I told you guys about this machine that scales perfectly, and that's this machine. So if it takes an hour to print one and I can fit 100 in there, it takes an hour to print 100. Those have to be small things. This build platform is 75 millimeters by 100 millimeters. So long as I don't want to print more than 3 by 4 inches, I'm probably okay. Another weird thing about this machine, it's the only one that I know of that prints upside down. Everything else, it prints on the top layer and then the part drops. Well, there's no room for the part to drop. This thing prints everything like this. So when you're done, you have basically your part hanging on to the ceiling of the machine like a bat. There is a support material that has to get broken away, much like the SLA machines. And like the SLA machines, it's the same material, so you do have to be careful. These can create amazing surface finish when the machines are up and running right. They are used widely in the dental and jewelry industries, as well as toy manufacturing. So all the action figures and children's toys, the prototypes get printed on a machine like this because the surface finish is so nice. So this will print down to 25 microns or less sometimes. you get to adjust the setting depending on how much time you have. So at 25 microns, there's very little finishing work that you have to do to get out a good looking part. And it may be kind of hard to see depending on your angle, but size-wise, here's 6 parts with a penny for reference. So I've printed out little medical parts that were meant to be dropped inside of your lungs to take looks around. It's good for small things, not great for big things. Material-wise, this much costs around 400 bucks. Everything's a consumable. So the lights inside the projector are consumable. The basements are consumable. The material's consumable. So it can be expensive to run if you're not taking care of things. But you know, there's machines in here that are $500,000. So everything's expensive to run the first time. Any questions about this stuff? All right.
You can only print it 2 inches by 3 inches. Why is the vat so big?
If I could only print 2 by 3 and there's no way to feed extra material in, I could only print things this tall. So you have that extra volume of the vat so that as you raise material out, there's still material there to print from. So it's kind of like if you dive into the pool, the height of the pool doesn't change much. Same idea. When I remove something from the pool, the height doesn't change, so I still have material in there. That's a good question. There is actually an option that, as far as I know, they never implemented. There is a thing on the back in this corner here where you're supposed to be able to stick a bottle of resin and it feeds itself. And the equipment's there, but they never enabled it in the software. So you could put the bottle there and it'll just sit there. It doesn't know what to do with it. Which is stupid. That's just stupid. Anyway, okay, let's switch rooms. We're gonna walk by one room and I will say that there's things inside. It's mostly just powder. And it's because there's no point for all of us to go in there. The machines in the next room, they require nylon, and it's a polymer that gets heated. So you need to keep track of how many times it's been heated, because the more you heat it, the more you change its properties. So we need to blend the material together at different stages so that we maintain a constant physical property of it. So the door will be open. You can look inside just to see what the equipment we use. Fancy things like a powder coating oven, not a powder coating oven, sandblasting cabinet. There is a cement mixer. There are some big blue drums. That's about it. It's not rocket science. All right, let's switch. All right. So these two machines are sintering devices, SLS. So this door comes down, seals. The chamber gets evacuated of air and it gets filled with nitrogen. So the nitrogen is generated by all the equipment on this back wall. So basically pressurized air gets forced through some filters, strips out all the oxygen, argon, stuff like that in the air, and leaves just nitrogen. We use nitrogen because it's easy to make, it's pretty plentiful in air, and it's relatively inert. So we want that environment to be inert because we want to control oxidization of the material. And it's an environment where there's powdered things and lasers. Powdered things are extremely flammable. So if you've ever played with like dried coffee creamer and a match, it's pretty awesome. There are plenty of videos online of people making huge explosions out of powdered wood dust and things. So we want to avoid this machine blowing through the other wall. Once it's sealed, all the air is removed and it's filled with nitrogen. It starts heating up, and it heats to just below the glass transition state of the nylon that's in there, which in our case I want to say is around 185 degrees. And the laser that's up top is there to give locally just enough energy to hit that glass transition state and liquefy. So as it liquefies, it turns into this nice little pool in the cross section that you want. And as it cools, it solidifies, and that becomes your part. So it's all sealed, heated, whatever. Laser shoots down, draws the picture that you want. The platform in the middle is the build piston. It drops. Platform on this side, in this case, will come up a little bit, exposing extra powder. This roller drags a new layer, or in this case pushes a new layer of powder across onto this piston again, and then it parks itself over here. Laser shoots down, melts stuff, it drops, this side comes up, new layer of powder across, and it just keeps doing that. These machines, this technology in general, are some of the most used machines for end builds, like things that you actually want to have functional in the real world. So it can be beyond a prototype, it can be the final part. They are capable of printing in all sorts of hybridized materials. You can fill the nylons with aluminums and glass and carbon and various things. And there are machines that also print in metals, aluminums, steels, cobalts, nickel, titaniums. Dental industry probably has golds. It's just extremely expensive to do so. This particular machine was the first machine commercially available, and it actually predated the commercial release by a fair bit of time. It was housed at Rocketdyne, and they were doing aerospace work for it, or with it. This machine has printed parts that are on the Space Shuttle and the International Space Station, which is kind of cool. Its serial number was 007, which is even cooler. And it was alive during the Northridge earthquake, and it fell through the floor, and they were able to hoist it back up and get it printing again. So it's built like a tank. Everything that's on them that looks pretty sturdy is, I want to say the door probably weighs a couple 100 pounds. This is a giant steel platform. And you can imagine that if we were printing in metals, this is what the build piston is filled with. So this would essentially be filled with powdered metal, which is essentially solid metal. So you basically need some sort of little forklift to get that out, or somebody a lot stronger than my flabby little arms, because I'm pretty sure that would weigh more than I do. On the table behind you guys, feel free to pick up any of the parts. There are plastic parts and metal parts. The various colored puzzle pieces are all different materials. There's a neat, kind of weird puzzle-looking business card thing here. This one. I'll play with that. That's awesome. You can pass this around. So those are printed as one piece. One of the things that is using this pretty extensively is lattice work, because you can create shapes that you could never manufacture. And this particular lattice is very squishy, which is pretty neat. Because you're printing in a powder, there's rarely a need for a support material, which means you can do living hinges and actual hinges, and you just use the powder to act as a bearing, then you blow it out, so you get bushings. So the business cards that are getting passed around are printed as one piece. They're not assembled. It's a gimmick, but it's cool. The metal pieces, aerospace, of course, and then medical. A lot of custom implants and things like that are printed on this technology because it's guaranteed to fit the patient. Not a whole lot of it happening in the US right now. The FDA, they're still trying to get it all approved. I believe the material is approved, but the process isn't. Outside of the US and the EU, you're good to go. You can fly over there and get parts printed for you. I don't know. Any other questions? Okay, so you guys are done. Thanks for coming to the lab.
Thank you. Thank you.